depends on how much is the delay in each arm of those. So you can get your S parameters that way, all right? You can obviously take the device to the laboratory and measure the S parameters and get them yourself. Now, the difference between this and that is if you put your field here, all right, eventually it comes here, and that will fringe in there, causing one port to be positive and the other port to be negative. As you can see now, the field will have to be in this direction. Eventually you get the field with opposite polarities here in this regard. Okay. So that's the kind of concept that you do in dealing with these devices. All right? Doing a field analysis even for this, even for a bend like this. Okay? Doing the field analysis is very complicated. Now, it's obvious that you can feed that into a three-dimensional simulator, electromagnetic simulator, and find the S parameters. Right? And those use several techniques like method of moments or finite elements or finite difference in the time domain or finite difference in the frequency domain. There are so many techniques in doing numerical analysis, and basically you enter the geometry and the material and let the package, the software package, come up with the field solution for you and show you what happens exactly, how these transitions take things into account, those sharp edges here. Okay, so that was one thing that I wanted to do. The other thing was the groove velocity. To study the groove velocity, or the velocity at which your signal or information propagates on the line, okay, what we do is look at the equation e to the j omega t, all right, e to the j minus j beta z for your wave propagation. And to get that in the time domain, multiply that by e to the j omega t and take the real part. So you eventually end up with cosine omega t minus beta z. Right? So what we've done for the phase velocity, we looked at this at different time instances. And we said, let's see how fast does this phase travel. And like we said, the phase travel is an apparent velocity, it's not a real velocity. So for that, we looked at this point versus that point, and both these points have the same exact phase. So the phase of this point is equal to the phase of that point. So omega t1 minus beta z1 is equal to omega t2 minus beta z2. And if you take t2 as t1 plus delta, and z2 is z1 plus delta z, just take them small increment here to get the differential element. You end up with omega delta t minus beta delta z is equal to 0, and from there we found omega over beta is equal to delta z over delta t, which we call the phase velocity. Right? And that turns out to be greater than this actually V, I'm sorry, C phase in the guide was C phase unguided, right? So that was the phase velocity. Now, what we're talking about here, suppose that signal is carrying some information, right? So the waveguide is carrying information. That means your omega is no longer a single frequency. What you have is omega carrying a sideband of knowledge, a sideband of frequency. So typically, if you're sending a single tone, it would be like that. If you're sending information, it would be sitting in sidebands. All right? Either single sideband or double sideband, whichever. All right? So assume now that we only have omega naught and omega 1. Right? And omega 1 here is your information signal. Right? If you develop the equations for that, you'll find that the group velocity, C group, which is the velocity at which this information travel, is the inverse situation here. It turns out to be C group in the guide times C phase in the guide is equal to C unguided squared. I'm not going to show the development. Few lines of equations that I will send in the Scholar site. Okay. Actually, I can refer you to page something in my old notes, and that way we can. Where is it? These are the best of functions. Here we go. Okay, if you go to my old notes and look, I don't have page numbers on it. Okay, anyway, I'll send that by email. I mean through the Scholar site. So based on that, we remember seeing C phase guide divided by C unguided, doing this kind of thing. That was FCMN, FCM1N1, and we saw it do this kind of thing, right? They will go to infinity at the cutoff and settle down to that. The group velocity does the opposite. And this formula here is to confirm that. One last final thing was the rectangular. So we can get into circular guides, I guess. That's also going to be in the old notes. Actually more than one thing. And both of these are in the old notes. The attenuation, I'm going to pull those pages out of the old notes and put them separate, so you don't have to struggle for them like I'm struggling right now. Should have pulled them out separately, but I did not. That's page 223. Where is 224? I'm missing 224. It's 231 here. It's 229. Okay. Can't find it. I pulled these staple apart to make it easy to find things, but I guess I made a bigger mess that way. I should not have done that. No, it's not here. Okay. If we go to the practical situation and start introducing the losses in the guide. Because so far what we've done was assume that the guide was lossless. We assumed ideal conductor, we assumed ideal dielectric. The reality of the matter is that you have some losses. Basically, you have surface currents because of the finite conductivity of the metal, let alone the dielectric losses. Okay, even with vacuum, or free space guides or air guides, you still have losses because of the finite conductivity of the surface. That's why the inner surface of the guide gets to be polished, very neat, and sometimes either silvered or gold, typically silver, to make sure that we have the best conductivity. Actually, silver conductivity is better than gold, right? So there is some losses in the guide, and that's because of the skin effect that you have in there. So if you go in the guide body here, right, your signal is going to penetrate, and we approximate the penetration by the skin depth. You know very well that the signal actually goes, attenuates exponentially down, and we average things to what we call delta. Delta is the skin depth. So there's the resistivity of the skin here has to be entered in the equations, and if you do that for the TE10 mode, you will discover here's the 10 mode, right? This one here is FC10, and if we said the next one will be the 20, because we do A is greater than 2B, right? We discovered that the attenuation almost goes to infinity right at the cutoff, and eventually dips down and start to rise again, right? This is alpha. So in this case here, the expression here now will have gamma, which is alpha plus J beta. And this alpha here is coming from the skin loss. The conductor skin, right? The bad conductor skin will introduce that alpha. That's different than the alpha in the cutoff, right? The alpha in the cutoff was below the cutoff frequency. But in the propagation mode, you get this alpha as a result of the skin loss. And typically that dips down at about 1.5 FC10. So to operate within a reasonable loss, usually we try to avoid working close to the cutoff frequency here. So typically we start at some F1 and end up some F2 here. And F2 minus F1 is what we call the bandwidth of the guide. The example I gave you before was the X-band waveguide, which is this one here. This is X-band, the 0.9 inch and the 0.4 inch. This is the one that you saw there. This one here is 6.5, and this about 13.1 gigahertz. And typically we do 8.2 to 12.4 gigahertz. If you take the difference between those, that's about 4.2 gigahertz. It's approximately half of your actual band here. That's about 6.5. 4.2, 6.5 is about half. So sometimes we say this is approximately 1.25 FC1, and this approximately 1.75 FC1. We leave about a quarter of the band as a margin on either side. Okay? So I'm going to refer you to those pages that show those equations and the diagram, and also the groove velocity, the guide bandwidth, the groove velocity. What else? A tabulation here of the waveguides and their cutoff frequencies, etc. Last thing that I want to do today, which actually wraps up the rectangular waveguide, is the resonant cavities. What we've done when we solved the equations, we did them assuming that the z-coordinate was a propagation coordinate, if you remember. So we ended up with kx squared plus ky squared plus kz squared is equal to omega squared mu epsilon, right? And kx squared, we wrote the solution on the x as sines and cosines, sine and cosine of m pi x over a, right? We did that. And we wrote the solution on the ky as sines and cosines n pi y over b. And we showed over the cross section that the distribution will be doing these kind of things, right? In other words, you have no propagation in the x or the y. And we assume the propagation to be only in z, because we assume the guide was extending. So we wrote the solution as e to the plus or minus j beta z. So if I take the same guide here that is traveling around any of these sections, all right? Okay, and then I short the two ends here. What have I done? I eliminated the propagation along z as well. All right, I created what we call a cavity. Okay, obviously the length of the cavity could be short or tall, depending. So if I do the same thing now, so instead of having walls on the x, walls on the y, I can also add walls on the z. So I create an enclosure now, and there is no preference to the z over the other two. So the z solution now maybe should be written also as sines and cosines. And we write that maybe p pi z over, let's call it d. All right? So now we have three parameters, m, n, and p. All right? There's no propagation along the z. We also have some standing waves. Just like we have standing waves here, we have standing waves there too. And basically, we can write here m pi over a squared plus n pi over b squared plus p pi over d squared is equal to omega squared mu epsilon. And whenever we have m, n, and p integers, obviously there will be some unique values for omega, right? You can sit down and write your tabulation here and find those omegas. Only for m, n, and p. If they are integers, that means you meet the boundary conditions, right? They were integers because the boundary conditions required them to do so. On the d also, to meet the boundary condition, that means the field has to be shorted here and shorted there. That means again you have to have similar situation, right? I'm doing a good job on the sinusoids or sinusoids, right? To meet the boundary conditions, again, the p has to be integer. So this must be integer, this must be integer, this must be integer. So obviously there will be some unique values for the omega that will meet that condition. Those particular omegas are the only frequencies that you are allowed to have a solution. If your frequency goes off any of these numbers, you don't have a solution, right? So only the integer numbers here that will give you solutions, so you have those frequencies. We call them omega resonances, all right? If you don't have the frequency that makes omega and the L, the L and C, right? Think about it that way. Omega squared LC is equal to 1. That's the resonance frequency, right? So if you put the L and C and put a different omega other than omega squared LC is equal to 1, you won't have a resonance. The resonance will be happening only at the frequencies that will meet that particular condition here. The equations are developed here, and you have a chart here that will show you the different modes of M, N, and P. Actually, this is for cylindrical guides. It's the same kind of concept. All right? It shows you the particular frequencies of resonance that can happen as a result. All right? Okay. Here's the rectangular, and this one here for the circle. These are the resonant cavities. So what you have here is a cylindrical resonant cavity, because obviously of the ease of machining, right? You can make a piston in a cylinder much easier than making a square piston in a rectangle. Here's a square piston in a rectangle. Someone was able to pull it out. Wonderful. Okay. So that's just the same kind of concept, except it's easier to machine them cylindrical or circle rather than rectangular. So that is the resonant cavities, right? And the expressions are all there. So what do we do next? Is we indulge ourselves into some cylindrical coordinate deviations of the circular guides, and for that we will need Bessel functions. Am I seeing any reactions to the word Bessel functions? Functions. Just another kind of function. So if you'd like, I will still have some time. My clock is, my personal watch is fast. All right, so let's get started with that. It doesn't, we can at least break the ice with the circle guides. Circular guides obviously are easier to machine and manufacture, and they have limited application compared to the rectangular guides. Like I said, if you want to do a resonator, a cavity, obviously circular guides are easier. Besides, if you do the analysis for the circular guides, you will be in good shape to do the fiber optics, because fiber optics require the same kind of math, just a little bit more involved, because you are dealing with dielectrics, and dielectrics will be tougher to involve because of the boundary conditions. You don't have the zero that you have there. So the circle guide, or if you want to refer to it as cylindrical, but circle is the typical name, you have a circle cross section. And that's your conductor here, and obviously you have to do cylindrical coordinates. Cylindrical coordinates, you have rho and phi and z, all right? So if I do my coordinate system like that, that's your x, y, and z. The cross section here will have the rho, and the angle phi is the angle with the x-axis. Right? So again, we start with del squared E is equal to minus omega squared mu epsilon. The development until this point here was not related to any coordinate system, it was just general, right? For H. Same kind of thing. Now we have to start working with cylindrical coordinates. So del squared in cylindrical coordinates is equal to 1 over rho, partial rho, of rho partial z. I'm sorry, partial. R of, let's say, E, so that would be E sub z. Plus 1 over rho squared, second derivative of E sub z with respect to phi squared, plus second derivative with respect to z squared. We are going to use the same separation of variable scheme. So we can write E sub z as a big rho function of rho, a big phi function of phi only, and big Z function of Z only. And if you put that in there, you will discover that you cannot separate them into three separate things right away. The Z, all right, looks like it's separable, but the rho and phi are mixed with each other. So we'll do the separation variable in two. It will take 2 steps to be able to separate things from each other. So I'm going to stop here because time is not enough to move further. But at least, you know, like I said, get something on the board in this regard here. What I'm going to do is I'm going to also put that on, so I don't have to do all the math here, right? I'm going to jump in between steps, so you can see the math online, but over here we can discuss the results rather than do the development. You have any questions before we go?
Lab reports.
What is that?
Lab reports.
Lab reports? I'm supposed to collect them?
Yeah.
Okay. He didn't tell me.
Okay. He told me to turn it in today.
All right.
So,
Okay. If you want to turn in the lab reports, I'll take them to the thing.
so I was going to try to let it a little bit, but I got home from work.